let's think about the next optimization. And the next optimization is trying to get data into cache early. So this is kind of the one technique where we can think about trying to combat compulsory misses or first-time misses. And what we can do is we can actually go and fetch data before we need it. And we can do this in a couple different ways. We can do this with just hardware doing it. We can do it with software doing it. We can do it with mixed schemes where hardware and software does it. And this really affects our compulsory misses. There's a note here I wanted to actually say something about. Instruction fetches are easier to predict than data cache accesses. And you'll actually see this sometimes show up in processors, where processors will have a instruction prefetcher, but will not have a data prefetcher. And it's because instructions, a lot of times, just execute instructions in a row. They're just sort of marching down instructions. And they just keep following through. So it's very easy to predict with high probability if you're executing, let's say, code at one block, the actual right next block will be accessed. So this is sort of the extreme of spatial locality. So if you fetch, let's say, block 1, you will go and fetch block 2 of your instructions. So you build a pretty effective prefetcher for instructions. So nothing is free in life. Prefetching can hurt you. So there are issues here. You really want your prefetching of data, let's say from your L2 to your L1, to increase your probability that you're going to find the data in the L1. But if you go and you pull in data that just wasn't useful, you're actually going to pollute the cache or effectively decrease the capacity of the cache with just extra data in there that wasn't needed. So you have to be very careful with prefetching, because it actually has the ability to get rid of compulsory mixes, but also has the ability to hurt the performance significantly. Timeliness is sort of an important issue here, is that if you go and prefetch too late, the data, that's not really useful. What do I mean by too late? Well, if you were to do a prefetch and the exact next instruction is the load that was going to use the data that you just prefetched, it's not going to save you almost any time. It might save you one cycle. So it's not really useful. But if you prefetch too early and then it gets kicked out by some other piece of data, it didn't do you any good either. It just wasted bandwidth up to your next level of cache, or to the next level of cache hierarchy. So it's a really tricky thing to get right here, this prefetching, especially on the data side. And of course, this this pollutes both the cache data, and it just increases the bandwidth out to here. So you need to make sure that you're not using extra bandwidth that you could be using for something else. So if you have a demand miss from your L1 out to your L2, you want to make sure that that always takes precedence over any prefetches. If we go look at instruction prefetching in particular, as I said, this is actually usually a benefit, because there's a high correlation. If you go request block I, you're going to go request block I plus 1 if it's not already in your cache. When you go to do this, though, you just don't want to go blindly request I plus 1 from the next level cache. You probably want to check the instruction cache to make sure you already don't have I plus 1. Because otherwise, you're just sort of wasting extra bandwidth that you shouldn't be using against your L2. Okay, so this is an interesting point here. This is an interesting optimization on the optimization of prefetching. Instead of just always filling, let's say, the subsequent block into the L1, you can build a little buffer here. This is kind of like it's not a victim cache, but it's kind of like an extra little cache on the side, or a fill buffer, or a stream buffer. And what's nice about this is you can basically fetch, let's say, I plus 1, put both of them in here, then try to maybe even fetch I plus 2, you're going to waste some extra bandwidth potentially here, or use some extra bandwidth. But if you, let's say, do a cache miss for that next line, it's already here. You can just try to execute right out of that, or fill right out of the stream buffer or the prefetch buffer. And this is actually a common theme, which is both used on the instruction side and sometimes on the data side, where people actually prefetch into a prefetch buffer and not into their cache. And they're just trying to do this to prevent pollution in their cache of data you don't actually ever need. But the data that's in this prefetch buffer, the stream buffer, has a high probability of being used. So it's probably a good idea to maybe even have one of those. Okay, so what are good heuristics on the data side? A couple different heuristics here. The most basic one is prefetch on miss. So if you miss for block B, go fetch block B plus 1. This is not saying on access. So if you go touch block B somewhere in the cache, this is not saying go get the next line. Instead, this is saying if you miss for block B, go get the next line. And that actually, people built a lot of those, and that actually is a decent heuristic. Another little bit more, one you have to be a little more careful with is the one when you're saying, if I access block B in the cache, let's say it hits in our L1 cache, should we go and preemptively try to get B plus 1? You gotta be careful with this one. Because you effectively can very easily be pulling in lots of data that you don't really need in your cache with this one, because you're basically, on every single load, we'll say, which hits in your L1 cache, you could very easily be pulling in lots of extra data. So you have to be a little bit apprehensive about doing this one. If you want to be more aggressive and you have big caches, though, you can be more aggressive, because it just really sort of hurts you in your capacity to go pulling more data. So if you go look at something like the Pentium 4 and beyond, so what's in your desktop possibly today, the Core i7, they actually have strided prefetch. So they will detect a program that is, let's say, accessing sort of data with given offsets throughout your program. So let's say you access location 1, location 128 plus 1, location 256 plus 1, and you're basically just sort of moving through data, but not just looking for the next line after the next line after the next line, but instead you're sort of looking with a given stride. And this is actually pretty common when you think about structures laid out in memory. So you take a C-style structure in an array, they're all going to be packed. And they're going to be packed by the size of the structure. And if you go touch, let's say, the first field of the structure. So you have a structure, inside of there, there's an int, a pointer, a floating point number, and you have a loop which says increment the first int, we'll say, in the structure. You're going to be striding through that memory. You're going to be touching the same location in memory as you sort of execute that loop. So what you can do is you can have something that's called a stride detector, and it looks at the memory references you do and tries to see if they're correlated somehow. And given the correlation, it'll predict, oh, if you just go and access, let's say, address 0, address 8, well, no, that's not an example. If you access address 0, you access address 128, access address 256, it'll predict and say, I bet you they're going to go access 128 plus 256, and just go pull that in early. hold that address information. So as I said, the Pentium 4 and the Intel processors have these stride detectors. If you go look at actually the Power 5, it has 8 independent stride prefetch detectors. So these things get pretty sophisticated. So you can actually go pull in lots of extra data. And this is important sort of in the care and feeding of the processor. So you don't have to wait for the cache miss. You can also do this in software just as well as in hardware. So if we go look at a software prefetch, you can add extra instructions to your ISA, which say, go get the data early. And this is kind of the akin, we've looked at doing things in hardware with hardware superscalars and VLIWs, which did a lot of that stuff in software. Well, you could do prefetching in software. But I should point out, to effectively do this prefetching in software, we changed the ISA because we added some sort of prefetch instruction. The other little trick that we had to do here, so if you look at this loop, I just wanted to say what's going on here is we're adding A of I, first we're multiplying A of I times B of I, but we're actually prefetching the subsequent loop iterations. We're prefetching the subsequent loop iterations data early. So you can do this prefetch for the subsequent loop iteration. But you need to have a few little twiddles here. You probably need to have a non-blocking memory system. Because otherwise, you need basically some way for this prefetch to go off the memory system and not just stall. Because otherwise, it didn't help you at all. So we'll be talking about non-blocking and out-of-order memory systems next lecture. But this software prefetch, you probably need something like that. I think we're out of time today, so I'll pick this up next time. Software prefetching, and then some other software optimization techniques. And we'll start talking about out-of-order memory systems.